seismic performance of confined masonry buildings. And in this session, I have two presentations, and I hope you received the notes. First one is to explain seismic behavior of confined masonry buildings. We talked about that in different contexts, in different lectures, but this is a small presentation to summarize it. And then there is a more detailed presentation on seismic behavior in performance in past earthquakes. When we talk about seismic behavior of confined masonry buildings, as we discussed, the main type of behavior is shear because of the nature of the confined and the, I would say, geometry and simply the way the confined masonry has been conceived and used from architectural point of view also is that the shear behavior is dominant. So, and mostly these are low-rise buildings. So anyways, the shear behavior is can be characterized by three stages. So when a confined masonry wall is subjected to seismic loading and in combination with gravity loading, first stage is to of damage is cracking inside masonry wall. So it starts in the center of the wall and propagates. Usually that is called diagonal tension cracking. And after that, with the further damage, with the further increase in loading, of course there are cyclic loading, so there are different intensity of the cycles of earthquakes. There is propagation of cracks in the tie columns, and that is when the force is that the maximum capacity has been reached once the cracks propagate into tie columns. And then every further loading will cause, I would say, more significant damage, and we call it, it's not a collapse, it is a failure. Usually none of the experiments on confined masonry walls resulted in a really collapse, but it results in failure, and failure is when there is a significant cracking and gapping cracks in the wall and in the confined masonry columns, in the tie columns. So these are the points 1, 2, and 3 on the diagram showing on the vertical axis we have that shear force, and on the horizontal axis we have horizontal displacement. So you can see that that there is linear behavior from zero, from the unloading stage, to point 1, where we have the beginning of cracking or onset of cracking, that is VM. And then we have further increase, which is at point 2, and then it is point 3, which is the failure point. This dashed line shows a contribution of masonry. That is what is believed. And the right, this extra increase is due to tie columns. So you can see that if there was no tie columns, the capacity would drop after the crackings. After point 1, there would be a immediate decrease in the capacity. That would be if it is unreinforced masonry. So here we can see a benefit of combining elements in increasing shear benefit or contribution in increasing the shear capacity of confined masonry wall. And as we discussed, it is all in design, it's all about shear capacity, and that governs. And also we said yesterday that in the design, we basically, the design equation is such that we design for point 1, not for point 2. So we are on the safe side in designing these walls. These are some, Professor Dr. Juan Jose Perez Gavilano on his lecture also showed some photographs of the testing. There were numerous tests of confined masonry walls, full-size walls in the different countries. There were some tests in Japan, for example. These are diagram on the left, and this is diagram on the right is test from Mexico. So you can see that the right-hand side is the stage of failure, that is the point 3. On the left-hand side is more like stage 2, where there is a cracking in the tie columns as well. On this left-hand side drawing, you can see horizontal cracks in tie columns, so there is some effect of flexure in that case because the cracks are horizontal in these tie columns, but cracks in masonry are due to shear. So also some tests studied the effect of the width of tie columns on the behavior of confined masonry walls, and it was concluded that it is better if tie columns, so this top shows 20 centimeter wide tie columns and the bottom shows 40 centimeter wide tie columns. So it is better if we have less width of tie columns, like the upper one. It gives better behavior. In fact, it is more characteristic of confined masonry. And you can see this blue blue line shows where the strat is. So this crack, so that is direction of the loading. You can see yellow line is direction of the loading because it was in one direction. And you can see that if there is a very wide tie column, like 40 centimeter wide, it's more like a column type dimensions, there is a much larger stiffness in the wall, and it simply the cracks don't propagate into tie column, but behavior has changed. So ideally, the size of tie column is equal to the thickness of the wall, as we discussed before. So in case of multi-story buildings, these cracks, it is important to say that cracks propagate at the same story level. So you can see that if this is a 2-story building, cracks would go from top to bottom of one panel of confined masonry panel or wall at 1 story. And you can see that what is the circled areas are most critical areas where cracking takes place. So these areas are very critical to be reinforced properly and confined with ties in tie columns. So in case of walls with openings, cracks will propagate to the openings. So this is a wall on the right-hand side, wall with window openings. This is something that you can see, it's not going down to the bottom, it goes to the edge of the opening. This is simply how the stresses flow in the building, in the masonry wall, and that stress concentration is at the bottom of opening. So this is typical for masonry. So these diagrams are from the ERI guide yesterday after the class. I hope you received annotated versions of the presentations or the lectures for related to design and construction of confined masonry, plus ERI guide, and I also shared Mexican guide, which is in English. So you can have that as a resources, but annotated lectures are important because there is some additional information beyond what was in the original lectures. This is an example of performance or example of this type of cracking and damage in confined masonry wall. This is from Chile. Next presentation will be mostly from Chile or performance of confined masonry after the 2010 Chile earthquake. This is a wall in a G+3 confined masonry building in Chile, or G+2 actually. And it is a ground floor level. So you can see that on the right-hand slide that how the crack propagated. This is with concrete blocks, confined masonry with concrete blocks. And you can see that the cracks propagated in a step pattern. And at the top, there is damage to the tie columns on both sides. Actually, this on one side, that there is complete disintegration of the tie column on the right-hand side, and there is a damage at the bottom. On the left photograph, you can see a damaged tie column, and you can see how concrete has completely disintegrated, disappeared from this tie column, and how the tie column has bent, reinforcement has bent in the top portion. In this building, this particular building had also issues with the quality of construction, so quality of concrete was not good. and quality of concrete blocks was not good. In that complex, it was a complex of many buildings, like 20 maybe, and one of them even collapsed at the ground floor level. So, but none of the other buildings collapsed, and they had some damage, different levels of damage, but no collapse. So in multi-story confined masonry buildings, I believe at the beginning and maybe the first lecture, we talked also a little bit about that, and you saw some examples of performance of multi-story buildings in the lecture by Professor Juan Jose, who showed some illustrations from shake table tests. Now we'll see some more. So what has been seen in the tests and also in earthquakes, that in multi-story buildings, damage is concentrated at the bottom level. So this has nothing to do with the soft story mechanism, but it is just the fact that if you have applied seismic loading at different levels, the loading is, in terms of shear forces, are increasing. On the right hand side, you have diagram of shear diagram for the building height. These forces are increasing from the top to the bottom, and the maximum forces are at the bottom. So the ground floor level in any confined masonry building will be subjected to the maximum shear forces, maximum bending moments, and maximum axial load. In your design assignment, you're also asked to draw a diagram like this. Diagrams like this are very important because they show us distribution of story shear forces, which is different from the applied loading, obviously. So that is the pattern of behavior, as I said, from the different tests, and also that was also observed in the past earthquakes. This is one of the shake table tests at Yuna, Mexico, which was done several years ago. And it was a G+2 building. It is scaled model with bricks, clay brick masonry. And this is the now I always show this. This is the testing. It was also, there published papers about this testing and the details of the testing. So so you can see this is the last stage of testing for that building. The building did not collapse. This is because you can see that the right-hand side wall, it was extensively cracked and damaged. So there were no further testing with this. So that is already a failure. So you can see there is extensive damage at the ground floor level in all walls that can be seen on this side, but there is no failure. And this was pretty significant. I don't know off the top of my head what was the intensity of acceleration at this magnitude of acceleration at this level. But there is, in fact, I can share the paper and, of course, video from this test. I know Professor Chaitanya requested earlier, so I can share with this. I will just write a note. So I haven't shared videos with you in this. And paper may be interesting. Paper was published at the World Conference on Earthquake Engineering in 2004. So all the papers published from earthquake engineering are available, but I can share it as well. So this is the damaged pattern, the illustration of damage of the building, where you can see more than one side, and you can see a damage in the walls. So in this direction, which is a longer wall, which we saw, this front facade, this is what we have seen. And the other is out of plane damage, because the building was subjected to loading in one direction only, in the direction of these longer walls. And in the cross direction, this would be then out of plane loading, and you can see some damage at the ground floor level as well, but more significant is in plane. More recently, also in Mexico, it is the same university, UNAM, which is their largest university in Mexico. It has 2.5 lakhs students. It's the largest university in the Americas, in the North and South America. They have done another series of testing. It was done by Professor Sergio Alcocer, who also did previous tests in 2004. And this is the shake table tests, and this is the video from the test. I believe that was the test. There is no more. This is a short clip of this video. So again, you can see a damage at the ground floor with the cracks. So this was in plane, and you can see some damage at the upper floors. And the researchers explained that by the effect of higher vibration modes, because this is a taller building. So there was some damage in the upper floors, but most significant damage is at the ground floor. Again, I have this paper, and in case you are interested, I can share paper to those two papers and videos from this testing. So this was done recently. Paper was published in 2019 at the conference. And it was published also last year at the conference, World Conference on Earthquake Engineering as well. So confined masonry in Indonesia, when I talked about examples of confined masonry around the world, I showed Indonesia as example as a country that uses confined masonry. So this is again showing, just to remind you of the practice. So in Indonesia, they construct confined masonry walls with half brick thick walls, and they're usually brick masonry. So you can see tie columns, you can see walls. That is their construction practice. So there was a project sponsored by Japanese agency to study a performance of confined masonry buildings in Indonesia, and testing was done at in Peru at the Catholic University. So this is the test. So subjected to, this is in a full-scale model. That was a smaller intensity shaking. This is Kobe earthquake, 1994. It was large intensity shaking. And you can see the collapse building. So this practice, as you can see, it's half-scale brick, not the full-scale bricks. It's a full-size one-room model. But brick size is it is like a wall thickness is 110 millimeters, and that is the same size of tie columns. And you can see also that we don't see any reinforcement. I guess there is reinforcement in tie columns hanging there, but it's very small size. They still had 4 bars, and but it is not a very good practice. Still, not too many confined masonry buildings collapse in Indonesia. In fact, they probably are a reason for not so high death tolls in their earthquakes. But they use confined masonry only for a single one, mostly for one-story buildings, sometimes from G+1. So they don't use them for apartment buildings. For apartment buildings, they would go to frame structures in Indonesia. They don't have code, but they use confined masonry since 1980s. They have some guidelines, and they still don't have a code, unfortunately. So that is it about this performance. I wanted to say that as I was indicating the chapters in the book which you have, that this topic is covered in chapter 4. So far, I haven't talked about chapter 4. in this lecture, I'm talking about chapters 4 and 5. So next lecture will be, a presentation will be about chapter 5. So chapter 4 is behavior of confined masonry buildings in seismic behavior and different modes of behavior. And chapter 5 is performance in past earthquakes. So this is the end. This is intended to be a short presentation, and the next one is longer. So both of them will be within this session. Any questions about regarding this presentation or not? Is it clear to you why there is damage only on the ground floor for confined masonry buildings, even though they don't have any irregularity? They're perfectly regular, but there is damage only on the ground floor. So that's important to understand that ground floor, it actually that may give, if you recall the lecture by Professor Juan Jose, he mentioned that in the taller buildings, they use reinforced concrete shear walls for the bottom floors. And that is the reason, because of the high seismic forces. If one wants to still do only confined masonry and has significant forces in a taller building, it could be possible to use thicker walls at the ground floor and or the first two floors, let's say, and then normal thickness walls, like 23 centimeters at the upper floor. So these are two different ways of handling the problem of not problem, but challenges of high seismic demand or high seismic internal forces in the walls, which cannot be met. The other option is, as we discussed in the previous days, is to change architectural design and add some more walls in one or two directions as needed, because it is all about the amount of walls, mechanical properties of masonry, amount of walls, meaning area of walls, which includes length and thickness, and mechanical properties of masonry, which give us that shear strength. So, okay, if there are no questions, let me move on to the next presentation, which is a part of this same lecture. Actually, stop presenting. I have to share just a moment.
Madam?
Okay, yeah, sorry, I disconnected. Can you please let me share the presentation?
Okay.
I reconnected now. It was by mistake. I disconnected. That was not. I just pressed the wrong.
Now you can present, madam.
Yes, and you can see my. Just confirm, please, again, that you can see my screen and that you can hear me.
Yes, madam. You are.
Okay, excellent. Sorry for this short disruption. So this, as I mentioned, The next presentation is on performance on confined masonry buildings in past earthquakes, and I did show in the initial very first day on Monday, I showed some examples of performance. This will be more like a case study of performance in the 2010 Chile earthquake. So most photographs are from Chile, and I will tell you, and I feel that it is really important not only to show cracks in the walls and all that, but to understand the whole context of their technology and practice, and then see examples of performance. So this is in that light, not just examples of in that sense. So because Chile is far away, I believe many or none of you were able to go there. It's really South America, very far from everywhere, I would say. So, and unless you go there, and really there are no books that explain Chilean practice and all that. So, anyways, I had the chance to go there. Actually, visited Chile 2 or 3 times, and once was after this earthquake in 2010. So I'll tell you a little bit about earthquake, a little bit about their construction practice related to confined masonry. They have interesting practice related to reinforced concrete too, but this is focused on confined masonry. So Chile, in 2010, February 27th, early in the morning, it happened like 3 o'clock in the morning. There was a magnitude 8.8 earthquake. It was offshore. It was offshore, not in the ocean. It was in the ocean, not on the land. It caused 521 deaths, even though magnitude of earthquake note is 8.8, close to 9. It had 5 collapsed buildings and 100 severely damaged buildings. That's all for the whole earthquake. And the other buildings, there were other buildings which had minor damage, definitely. So those 5 collapsed and 100 severely damaged buildings had to be replaced. Out of these 100 severely damaged buildings, they were mostly reinforced concrete buildings, actually, and some were confined masonry. So these were not only confined masonry. And so approximately 1% of the total building stock in the earthquake affected area was either damaged or collapsed. So 99%.
Excuse me, madam.
Yes.
Just have you saved the screen?
Yes. Just let me see. I maybe shared the wrong screen. Let me see. I will stop sharing. Let me try again. So let me see now what I'm doing. So I will now try to share again. So I will, let me go. So if I share the screen, I share desktop. Can you see now my screen?
Not yet, madam.
Not yet. So I'll disconnect and I'll connect again. That may be the safest way. Let me do that.
Okay, madam. Madam, now we can see the screen.
Okay, I'm muted. Okay, that's okay. So that's good. So let me start again. I'll just repeat first few slides briefly because you couldn't see them. So you couldn't see any of my slides from the presentation. I haven't started talking about it. Was just talk. So I'm just on the second slide. which is good. So the presentation is, I'll show the first slide so that you can see. I'll repeat it also. Okay, so you can see this this slide now full screen.
Yes,
Okay.
madam. It is visible.
Yeah. So that is as I said, the topic is performance of confined masonry buildings in past earthquakes, and it will be a case study of Chile earthquake of 2010. The earthquake happened on February 27th, 2010, very early in the morning. At I believe 3:30, around 3:30 a.m. when most people were sleeping. Magnitude 8.8 earthquake. It caused 521 deaths. Out of this, 100 died in tsunami, due to tsunami. There was a tsunami immediately after the earthquake in Chile. And only 5 buildings totally collapsed. There were 100 severely damaged buildings, and then there were others which were less damaged. But in total, only 1% of their total building stock in the earthquake affected area either damaged or collapsed. So it is just the area affected by the earthquake, not the whole country. Okay, so Chile is a country, if you look at the map of South America or America, it is a country that goes parallel with the ocean, so it's very elongated. And you can see here these different earthquakes in Chile. And the epicenter of this earthquake was very close to, for example, city of Constitucion. And there was another city, but anyways, it was offshore. And there were smaller cities close to the earthquake, not the big city. The bigger city is Santiago here on the top. That is the capital of Chile. That is really big city. And this earthquake caused the significant damage of reinforced concrete buildings in Santiago. Which is about 400 kilometers. So this is a subduction type earthquake. Chile is located in the subduction zone. Those earthquakes are very high intensity magnitude, and they have earthquakes of intensity of magnitude more than 8. I would say they had one in 1985, and then they had one in 2010. So, and they have magnitude 6 earthquakes every 10 years, 6 or more. And the country is pretty populated, so there is no area which is not populated. So wherever earthquake strikes, there will be affected area. It's not a big country. So here you can see map of intensity of the earthquake. So maximum intensity, that was according to the MSK scale. Intensity in Santiago, if you go to Santiago, it would be maybe 6, but it caused, as I said, damage of 20-story reinforced concrete buildings. In other places, it caused intensities 8 and even 9, close to the 9 here, the black. I went to the city which, and I have photographs from city Constitucion, which had intensity of 9. And then I also visited cities that had intensities 8 or 7 in this earthquake zone. So there is a paper that discusses intensities after the earthquake. They are very good at doing this type of analysis after every earthquake in Chile. This is again population exposed, and this is where Chile is actually on the map of the world. But anyways, again, another map of intensity. This was done by Americans. The previous one was done by Chileans. And this is according to the MMI scale, I guess. So the 2 different intensity scales. So anyways, the cities in the coastal area close to the epicenter experienced maximum damage due to earthquake. Plus there was a tsunami which happened about 1 hour after the earthquake. Over 12 million people were estimated to have experienced shaking of maximum of intensity MMI, modified Mercalli intensity 7 or stronger, which is about 72% of the total population of Chile. So Chile is not a large country, so if 12 million people were 72%, it is like total population of Chile is less than population of Delhi, I guess. But it is populated country, so it's small, but the territory is also small, so it's populated. You can see cities, villages, townships everywhere. So confined masonry construction in Chile, that is the background I wanted to give you, because it's, as we know, that masonry in general differs, masonry construction practice is very different in the world. And so is confined masonry in a sense. It's not the same in Latin America as it will be in Asia, for example. So confined masonry is widely used for construction of low-rise family buildings, single-family buildings like these bungalows, one up to 2-story high, and also medium-rise apartment buildings, 3 to 4-story high. That is typical in Chile. I think they can go higher than that, but that is their practice of these apartment buildings, medium-rise apartment buildings. If they build taller apartment buildings like as I said, 20-story buildings they have in Santiago, they would be of reinforced concrete and they would be shear wall structures. So in Chile, they don't use frame systems almost at all, reinforced concrete frames. So confined masonry construction practice started in 1930s after the 1928 Talca earthquake, which had magnitude 8. I believe that again in that earthquake there was already some confined masonry, and it could be explained that there is lots of Italian immigrants in Chile, and it is possible that they started confined masonry practice because the first example of confined masonry was in Italy after the 1908 Messina earthquake. So good performance reported after these earthquakes in 1930s, like Talca and Chilean earthquake started this practice, was the cause for the confined masonry practice in Chile. There was no other reason, and from that time, from 1940s to almost 1990s, they did not have any code for confined masonry, but they had some official government issued guidelines, like but it was not a code, it was not mandatory. So only 1990s they have first code for confined masonry. The area affected by this earthquake from 1988 was also exposed to several major earthquakes. Obviously, it is the high seismic area. And it was, for example, in 1985, that same area was subjected to magnitude 7.8 earthquake, which also exposed both masonry and concrete buildings in Chile, in the whole of country. So good performance of track record in past earthquakes before this earthquake of 2010 was mostly based on 1 to 2-story buildings. But in 2010, for the first time, the taller confined masonry buildings were exposed to an earthquake in Chile, to a really strong earthquake. They might have been exposed to, let's say, magnitude 6 earthquake, but they don't consider those earthquakes as very strong. So 3 and 4-story confined masonry buildings the construction of these buildings started in 1990s, which means after the 1985 earthquake. And as this is frame portions says what I already repeats what I said, is that the modern masonry codes in Chile were first issued in 1990s. Before that, there was a document called Ordenanza for some guidelines or order for urban planning and construction, so they did not have a proper code. So without the code, they still followed the practice, and it was good. So by and large, so performance of confined masonry buildings in the earthquake, in that earthquake of 2010, confined masonry buildings performed well. Most 1 and 2-story buildings did not experience almost any damage, except for a few buildings which suffered moderate damage. So there was no collapse among those buildings. And also large majority of taller buildings like G+2, G+3 buildings remained undamaged. However, a few buildings suffered severe damage and 2 3-story buildings collapsed. Only 2 buildings, 2 confined masonry buildings collapsed in this earthquake, and they were both 3-story buildings. So here is what they use mostly as masonry units. They use these hollow clay blocks. You can see on the left side, this is from after the earthquake, so it's damaged situation, but you can see these blocks, so they are not reinforced. Horizontal reinforcement is possible, but I don't think it is used widely in Chile, but it is possible. And older buildings have clay bricks. So they, in any case, there's a clay elements. They are in some cases concrete, hollow concrete blocks are used, but that is, I think, very, very small a percentage. Most buildings that I've seen in Chile have these clay blocks, which are shown on the left-hand side. This is, yeah, concrete block. Concrete blocks in Chile, like in many other countries, are of poor quality. They're not good quality. So here is an example of when I was there after the earthquake, I saw construction of confined masonry. Here you can see concrete. They have a concrete plinth or concrete foundation, and then these are tie column reinforcement. So you can see examples. These stones, I don't think, maybe they're part of foundation. Could be this was still foundation level. This is masonry construction in progress. This is a small city. So you can see it is single half brick, looks like half brick thick wall, and it's brick masonry, not block, not this hollow block, hollow clay block masonry. So they do use bricks, but most constructions are with these blocks. So they in this construction, that is the same building, you can see examples of tooting. I showed this photo before to exemplify tooting. So you can see tooting with two bricks together. So this is like two bricks, and then there will be two bricks with exposed portions. So, and you can see they have horizontal reinforcement also at some locations, which also improve this bond between masonry and concrete. Here you can see, for example, how small is this cage, reinforcement cage, because if this wall is 110 centimeters thick, so the cage is much less than 10 centimeters to give the, and you can see that same building, how the wall, and you can see that leather reinforcement, how it is sticking. They will cut it off later, I guess, and you can see that it is placed only at some locations, so it's not every, so it's maybe at 40 centimeters or 50 centimeters. So they had both tooting and that reinforcement for some reason. So they might have reinforcement continuous along the wall length. So it's not just at the intersection locations, it is a horizontal reinforcement. But I cannot see a location of other bars. So anyways, it is not heavily reinforced in horizontal direction. And these are very small wires practically, as you can see very well from these photographs. Steel reinforcement, common steel grades are this kind of mild steel with the grade of 280 MPa, and the higher, this deformed steel or Tor steel as called in India, with 420 MPa. And then they have high strength steel, which can be used, which is used for tie beam and tie column prefabricated reinforcement cages and leather reinforcement, and yield strength is 500 megapascal. So in Chile, like in Mexico, there is a prefabrication of reinforcement cages that is commercially available, so they don't have to make them at the site. So these are reinforcement cages. This is from one of their catalogs. So you can see that you can order the cages with different tie sizes. So in this case, tie size is only 4 millimeters. So I have seen many examples of small size ties, diameter ties like 4 millimeters, but they also, in the right hand side, they have 8 millimeter ties. So or they have 8 millimeter bars, but ties are still 4.2. So these prefabricated cages use very small size bars and small size ties. So these are some examples of cages, but this may not be, the cages here on the photograph may not be prefabricated, but I just showed how they have a prefabrication practice. Floor systems in Chile, they have wood floors in single-family buildings, or their wood roofs in single-family buildings which are 2-story high. So even in confined masonry, they have wooden floors in these single-family buildings. They could have, or they're concrete floors in 3-story high buildings and up, which are either cast in situ or precast. They use precast floors, which consist of hollow masonry blocks, precast RC beams, and concrete overlay, and commercially known as trellis system. This system is also very common in Europe. I will show that is that system, trellis system. It's common in Europe, not under that name. There are different commercial names, but you can see the reinforcement that is running running between these blocks, and then hollow masonry blocks, and then it is all cast with concrete, poured concrete on the top. So it is semi-prefabricated, let's put it that way, because it's combination of prefabricated elements and cast in place concrete. So cast concrete is very important to provide this continuity of reinforcement. So this is example of that system. So you can see reinforcement in this steel reinforcement, and you can see these strips of where this reinforcement is, and you can see transverse elements are made of masonry, and then there will be concrete on the top. So this system is very common in Chile. It did not have any problems with performance of this floor system in the buildings. So all buildings like this would have that system. And at the top floor, because this is they have heavy rains in the winters, they have sloped roofs, so they have timber roof structure, and they don't have a floor, this precast floor at the top level. So it is only a tie beam that they have at that level. So this is the roof structure, timber structure, lightweight roof. So single family rural house, you can see again, it does not have a concrete floor. It has a gable wall, which is made of timber, and it has lightweight roof. And but you can see a significant tie beam at the roof level. So it has some form of rigidity at the floor, at that roof level or at eaves level, provided by this tie beam. So then there are 2-story, the typical construction besides these isolated buildings. Very common are these, maybe we call them houses in a row, or that are all connected, or they call townhouses. So they have small plan dimensions. This may be some form of social housing, so these are not very large buildings. Or I mean, the total building may be large, but the size of individual dwellings is not very large. So it has ground floor and upper floor, and the plan dimensions are only 5 by 6 meters. So 5 in one direction, 6 in the other direction for a single dwelling, and then they have 2 floors. So it's a small area total, but some families live in those. Typical damage patterns in those buildings are, you can see a separation crack, horizontal separation crack at the top, above the top of this tie beam, and the beginning of the gable wall. A gable wall would be here lightweight wall. It was always made of wood or plywood, and so it is not going to collapse. It doesn't collapse. It could be some separation. We have not seen any collapse of these gable walls, and then a roof is light. In the building, inside the house, that is one of these buildings that I've shown in the previous slide. We visited the building inside. People were leaving. It was I visited Chile in July 2010, and the earthquake happened in February. So it was 4 months after the earthquake. So people, of course, occupied their houses, even though you can see clearly shear cracking in this wall, in plane cracking. they just, or somebody secured this with some props, and they continue to live. You can see they have flowers on the table and all that. So they were waiting for government to help with the repair of the building. That is it. Some noise is there a little bit, so can you please mute yourself? Thank you. So here there were no tie columns at the openings. That's what we observed, but probably the damage would be there in any case because of intensity of earthquake. And these buildings that we visited were all in the epicentral area of the earthquake. So this is more or less all I could say about these single family buildings. As I said at the beginning, small, very minor damage, no collapse. The buildings were repaired after the earthquake, and they were not retrofitted, just repaired. The cracks were sealed, and they were replastered, and that is all. In medium-rise buildings, so in Chile, they also have a social housing program. So many buildings, it is not a fully socialist country, but it used to be socialist, and from that period they have this extensive social housing program, so that for people who are among the poor, they poorer sections of the society, they provide housing for them, and they would be in these confined masonry buildings, which are, you can see an example, G+3. You can see external staircase here. So they might have some cases external staircases, but they have also internal staircases, so it's not a rule to have external, but you can see it's confined masonry, and I've seen many buildings of this type in Chile. In this size, this height, as I said, G+2, G+3. Typical damage patterns in these buildings is in-plane shear failure of masonry walls and damage to reinforced concrete confining elements, particularly tie columns, depending on the extent of damage. If you remember the first slide in the previous presentation, you remember these points 1, 2, 3. Point 1 is internal cracking in the masonry wall. Point 2 is when the wall reaches capacities, when we have a damage in reinforced concrete tie columns. So it all depends how strong was the shaking at the location, and also what was the amount of walls in that building. So in Santiago, which, as I said, it's about 400 kilometers from the epicenter, but the recorded peak ground acceleration from this earthquake was about 0.3 G. It's pretty high, so that's why the buildings were damaged in Santiago, even though earthquake was far away in that sense. So this is also complex of confined masonry buildings, older confined masonry buildings, and the damage was observed at the ground floor level. And you can see damage cracking. This was all shear cracking, and this is cracking between in the piers between two openings. So you can see plaster has fallen out. There is a damage, but this was probably repairable damage, and building was continued to be used after the earthquake. In fact, it was used. I was there after 5 months, and people were living in this building, so they were not vacated. So in the same complex at one location, there was a damage at the upper floor, but this may be because the bottom floor, the floor below, had openings, so maybe there was a concentration of damage at the upper floor, since the bottom floor was not able to receive the forces, so that could be explained, the damage at the upper floor. So there was discontinuity between the floors. You cannot see now the bottom floor entirely, but you can see a damage, and this is a typical shear cracking of this confined masonry panel, which was going from the end of the building to these first openings to the balcony. Then this is the same complex of buildings, and somebody has drawn a pattern of damage patterns for these buildings. So you can see because see, this is balcony level, so there was ground floor level, second floor level, and you can see lots of openings at the ground floor. And then, so the damage, more damage was concentrated in the upper floor. So that is an example of if there is no sufficient amount of walls at the ground floor, damage can move up at the upper floors. But in any case, it was repairable damage. These are all different photographs of damage, which was compiled by Chilean colleagues, and you can see typical patterns which we discussed before. This is again non-confined opening, confined openings. I talked about that before. I think I showed these photographs in another context. This is a building in the epicentral area. City is called Caquenes. Let me see if I can show you where is Caquenes relative to the epicenter of the earthquake. Maybe that is important for you to visualize. So I can show it here, Constitución. Next slide, maybe. It doesn't show. Caquenes was in intensity 8. That is the city intensity 8. So it is in this zone close to the, really close to the epicenter of the earthquake. So the largest intensity according to MSK scale, which is used in Chile, is 9. That is really at the epicenter or very close to the epicenter actually. And then Caquenes is 8. So it is the city which was exposed to very high intensity earthquake. Anyways, the building that I visited, we visited, I was going with my 2 Chilean colleagues from University of Santiago, University of Chile in Santiago. So this is very elongated building, G+2 apartment buildings. This building was vacated and was intended to be demolished. So this is that heavily damaged building. You cannot see here from the fence that ground floor experienced extensive damage, but I will show you now in the next photos. So this is the damage at the ground floor. They had the walls were constructed using these hollow clay blocks. They did not have properly constructed tie columns. It was confined masonry, but not followed to the rule. For example, you can see this door first to the left. There was no confined masonry. It was just masonry. You can see that there is no confined masonry at the opening. So this door opening, it was not confined. So the rules were not followed. So that is definitely one reason for being there. This is inside that same building. You can see that even interior walls, which were also of confined masonry, they were suffered extensive damage. Again, you can see the damage of these hollow clay blocks. You can see that the parts of walls were missing. The building did not collapse, but this state of damage would be called near collapse or close to collapse, and it had to be demolished because of extensive damage to so many walls in the building. This is again the same building. I guess, yes, it's the same building inside. So interior walls were very widely spaced. So there were few walls in both directions. And I unfortunately don't have plan of the building. Here you can see a floor system, which is the same as I explained before, Tralix, commercial name Tralix, that composite system consisting of concrete and masonry. And this is now another building, showing that is a building in another city where there was a complex of 17 buildings and one of them collapsed, and I'll show you that. And in that complex, they were using concrete block masonry, hollow concrete blocks. And again, you can see a heavily damaged wall. You can see how tie column at the top completely separated from the building, and heavy damage of concrete wall. This is the same building as before in Caquenes. That is interesting. This is out of plane damage. In the next lecture, we'll talk about out of plane performance of confined or behavior of confined masonry walls, and that is in the next session. But this is an example of the building where we could see a damage out of plane. Because this direction was the longitudinal direction was subjected to in-plane seismic loading, and this was mostly out of plane. So you can see the type of cracking. This is the most damage I have seen in the out of plane direction in any building in Chile. So, so damage is second floor level. Building had a timber roof at the top, and this is now a little bit about out-of-plane damage. The same building at the top level, they had a tie beam, but it was not robust enough. So at the top floor level, again, there was a damage out of plane. So you can see that kind of that pattern of forming these yield lines in masonry, like this failure mechanism for out of plane. And so that this, in conclusion, this building suffered both extensive in-plane damage at the ground floor level and out-of-plane damage, which is concentrated at the second and the third level of the building. This is example of cracking, and you can see that the crack has extended through that tie beam, but the tie beam was not very large and at the roof level, and then there was a timber floor, timber roof structure. So this is another example. You can see that the crack and another detailed crack expanded through the tie column in that case. This is some other buildings also in showing the damage at the tie column at the base, so-called toe crushing failure mechanism. So you can see here how tie column reinforcement buckled, and there was a very small tie, that is maybe that prefabricated elements with 8mm bars and 4mm ties, which were at 20cm spacing. And you can see how this masonry block crushed completely. So these masonry blocks are pretty brittle as far as masonry as behavior is concerned, but they have sufficient strength and could perform well in most cases. Okay, so tie column failure, I showed this photograph already. So this is now examples of tie column failure and tie column failure of tie column. So there are several examples. I'm just grouped them here on tie columns, and you can see here detail of this failure. So you can see that there is no reinforcement in tie beam that goes around tie column. In the detailing section, maybe I did not emphasize that, but at the edges of the building at the exterior, and it is important that the reinforcement from tie beam goes around. There is that U-shaped bar that goes around. So otherwise, there could be a separation of the, it can be, and there is no other ties in this area of the tie beam. There is no horizontal reinforcement. So this, in conclusion, this wall was not adequately reinforced. And then secondly, the tie column was not adequately reinforced. And secondly, there was use of low strength hollow concrete blocks, and that could explain the failure. So causes of damage in these buildings are inadequate wall density or wall index, because where we noticed we did not calculate wall index. We did not have time to do detailed measurement of the dimensions, but there were very few walls inside. Like besides exterior walls, there were very few load-bearing walls inside. The buildings that were heavily damaged, then we observed poor quality of masonry materials and construction. Construction quality was also not very good in many cases in terms of concrete construction quality and masonry construction quality, and inadequate detailing of reinforcement in confining elements. By that I mean spacing and size of ties, for example, in tie columns. In many cases, there was absence of confining elements at particularly large openings, such as doors, and there were some building layout issues also observed. But I would say these first few reasons are most predominant. And there were some geotechnical issues. So what was shown, and I mentioned that when we talked about wall density or the wall index simplified method and wall index calculations, is that low wall index values per floor of 0.5 to 0.7% were observed in severely damaged buildings. So that is what I meant by saying that. And the second, poor quality of masonry materials. You can see here poor quality of concrete block, and the blocks were tested. They had very low strength. And then brick masonry, you can see very thick joints in some cases. And probably low strength bricks. So that exists everywhere. And then inadequate anchorage of tie column reinforcement. Let's say this is a corner building, single story, but corner building. And you can see here how reinforcement stops at the end of tie beam. So they didn't have any additional bars to connect these two beams, so tie beams, because it was going under an angle. So, and you can see also for tie column reinforcement that was discontinuous. There was no lapse, so very poor quality of construction and poor quality of concrete as well. So that is the reason of damage, but you can see here 4 months after the earthquake, this building has been used. People are sitting there, and it has not been demolished, so it's that damage. This is again in Santiago, in 400 kilometers from the epicenter. There was some damage of in tie columns in a confined masonry building. This is confined masonry building with some graffitis, but the damage is at the top level. In the circled, you can see a red circled part, and you can see how the reinforcement was not continuous. You can see that hooked bar. You cannot see any ties in or stirrups in tie beam. So it was not properly constructed. So there was a deficiency in construction, and maybe it was a design deficiency as well, but definitely construction was not done adequately to have all the features of confined masonry. So this is details of the drawings. These are the drawings from Chile. They're showing how the ends of the reinforcement at the intersections should be anchored and continued. So all details are there, similar as what we discussed about Indian code, but they may not be followed in all cases, just the same cases in any other country of the world. So this is tie beam. This is not for that building. It is from some other building which we visited. And again, this is if you have a tie column to tie beam connection. So this is a tie column, and then there is a slope tie beam. Again, there is a special detail showing how to continue reinforcement. So there were additional reinforcements. So in this case, that is interesting. They use prefabricated cages for both column and beam, but they added bars in this area for continuity. So that is a good way of using these prefabricated cages and adding the bars as needed to make good details. So they have pretty developed this tradition of fast construction, I would say, in confined masonry with prefabrication of cages. These are some details of anchorage, which involve 90-degree hooks. This is what I showed you earlier, and this is something that they implemented or they had in practice, but not always. Here you can see again another detail, another example of poorly detailed joint, tie column to tie beam joint. You can see again that there is no reinforcement. Very critical at the end to have bars, horizontal bars from tie beam going around these bars in tie column. So joint, even though it is not moment connection, the joint detailing is important because there is, once this shearing of a tie column happens in that area, then this joint area becomes also vulnerable in all cases. But that is at ultimate stages of behavior when there is a really significant major earthquake and the building, the walls, the structure is exposed to very high shaking. This is an example of complete lack of tie column, the ties in tie columns reinforcement in this area. You can see vertical bars, but you cannot see any ties in this area, and no wonder that it was damaged. It's not a surprise to engineers. These are again some details of drawings. The details of these are prefabricated specified on the drawings to have prefabricated cages with 8mm bars, and so this seems to be typical prefabrication, 8mm bars and 4.2mm ties. So this is a note smaller size than what is recommended for India in the code, but they permit that. The spacing is though 15 centimeters as opposed to 20 centimeters in India. Additional ties are placed at the site to do that. These are some absence of confining elements at the openings. We have seen that many times. Here you can see this building which has been damaged and will be probably demolished. There is no collapse here. You don't see visible damage in confined masonry at this side, but there is at the other. But you can see that there is a lack of confining elements at the opening. So I believe this building would be or was demolished later on. Yeah. So absence of confining elements at the openings, you have seen that already. There's no confinement. You can be clearly seen that there is no reinforced concrete at the opening. Now, the buildings in Kaukanes, the one that I've shown already, is circled here. That is very interesting. The one with red paint, which was heavily damaged, it is circled here. However, there were 3 other buildings in the other direction. They were not under 90-degree angle because these were 2 streets, and these 3 other buildings were in the other direction. And they were constructed at the same time by the same builder. And what is interesting is that we visited that building that was damaged. I already explained, and that documented the photographs of damage both in plane and out of plane, but that was severely damaged. But the other 3 buildings, which are here circled in black, we visited them. They were moderately damaged to no damage. So because they were in the other direction, so predominant direction of earthquake loading was along the longitudinal direction of this damaged building. So these other buildings were not damaged. That is interesting. Confined masonry buildings we just discussed in previous presentation, collapse mechanism or damage mechanism, that it is always at the ground floor. And I'm now showing you 2 collapsed confined masonry buildings in the earthquake. I mentioned that there were only 2 buildings that collapsed, which collapsed in the earthquake. And they're both 3-story high, G+2. One is in Santa Cruz, which is maybe intensity 7, and the other is in Constitucion. That is that place marked with black with its intensity 9, maximum intensity of the earthquake. Most damage was concentrated at the 1st story level, and 1st story collapsed. This is the Constitucion, the city which is intensity 9. It is a street, and then there is a slope. So these buildings are on the top of a small hill, and below that hill there was just a sloped ground with some greenery. This is north, so the north direction, maybe not relevant. So there were several buildings, more than 3, but you can see here at least 3 buildings, roof levels of these 3 buildings. And this A, we will label them A, B, and C. So there were buildings A, B, and then C is the one that was most heavily damaged. So, so that is the sloped ground, very steep slope, more than 45 degrees. So it was location is on the hill. On 2 sides. So 3 buildings A, B, and C. So these are buildings A and B, which were damaged, and building C, which collapsed. And I'll show you that is the location of outside the building. Building C is on the left side of this photograph. No, actually, building C is behind this. You can see these clothes, and so behind the clothes is building C. So you can see now that building C has 2 stories. whereas buildings A and B have 3 stories. That is because the ground floor in building C collapsed. They were identical, completely identical buildings. So this is a plan view of these buildings, of the collapsed building. And in this collapsed building, they had different sizes of tie columns. That is interesting. This marked with red or 14. So they had 15 centimeter thick walls. They were these hollow clay walls. These red colored tie columns are 15 by 15. Blue colored are 20 by 15 or 14, actual thickness is 14. So they were longer, they were rectangular sections, so that the corners they made longer, larger tie columns. Then P4 is brown, it is 15 by 15, these are interior, on this interior wall. Then this P5, which is black, this is a 70 by 15, it's also reinforced concrete element here in the middle. And then P6 in this direction is 90 centimeters by, so it is like a small wall practically. So they had at 2 locations, one in each direction, they constructed I would say elongated columns, 70 centimeter or 90 centimeter even length, which they reinforced and all that. So this is interesting strategy. And you can see the walls of course, exterior walls are clear, and you can see interior walls, but there was no confining elements in any of the interior walls. So the confinement were only at the exterior walls. Actually, I think some of these walls had, but it was not marked as a confinement. I'm sure that actually some walls had confinement, but that is not labeled. So anyways, so the size of the building, if you can see, the overall width would be about 10 meters, 8 meters, and the length would be, this is one block of a building, the length would be about 12 meters. So it is 8 meters by 12 meters. This is more or less 2 apartments, I would say, 2 apartments in this block at ground floor level. So the building C collapsed. It collapsed. This is the building C tie beam. It says block 7. That is a tie beam at the top of the first floor. It collapsed and it moved in this direction of the yellow arrow. So original location of the base of the building was this red line. So it moved by about 1 meter but in collapsing. And you can see the tie column at the ground floor level, which obviously collapsed. You can see crushed bricks. So moved by approximately 1.5 meters towards north. So collapse was in the towards north direction of the of the north direction, just and this length. So this building was located, this block C was located just, this is my colleague Maximiliano, and behind him is a cliff. So he was standing, and this is a student who was standing next to the building, collapsed building. So this length is about 5 meters. So it was really close to the top of the hill, and it is believed that the fact of the dead block was closest to the hill caused the amplification of ground shaking and the highest shaking in that building compared to the other buildings which were further away from that top of the hill. So probable causes of collapse are geotechnical issues. This building is localized influence of the slope, boundary, and variations in subsurface strata might have generated localized variations of horizontal and possibly vertical ground accelerations. And second, inadequate wall density at the calculated wall density at the ground floor level of wall index was less than 1%. And it is very high seismic zone. Obviously, it was in the epicenter of magnitude 8.8 earthquake. So the other case is a collapse of a 3-story building in Santa Cruz. It has a smaller intensity. That location maybe 7. 6.6 to 7 of, and you can see so many, I think 17 buildings which were identical in that complex. And in that complex, one building, this is the building that collapsed. So you can see all the other buildings are G+2, and this one had 2 floors. It fully collapsed at the ground floor level. So it just lost ground floor and then collapse took place. So that is the collapsed building. You can see no ground floor. And then, of course, due to the collapse, the upper floors were also damaged. But this was with concrete blocks. And I showed you some photographs of concrete blocks. So in this building, there was poor quality of construction, both brick and concrete. There was a mix of brick and concrete block masonry. You can see thick joints. Brick quality was very very low. And also, the colleagues from Chile calculated this wall index. It was less than 1% per floor as well in this building. So only 1 out of 32 buildings in this complex collapsed. So it was 32 buildings which were completely identical. And both in case of this building and the previous building in the other city, there is also an indication, but it was not confirmed, that there was some renovations done at the ground floor level, and that some of the some openings were created in the load-bearing walls at the ground floor level, and that could have also contributed to the collapse of these both buildings. So that is all. Acknowledgements to my colleagues Maximiliano Stroza and Maria Ofelia Moroni from University of Chile. We were together, a team visiting for 10 days the earthquake-affected area. And I have collected lots of photographs, not only from confined masonry, but from reinforced masonry and also reinforced concrete. And it was sponsored by Earthquake Engineering Research Institute. And we published also a paper, and it was published on the, I believe you can find that report on the Confined Masonry Network website, which I already mentioned to you under Chile. So in Confined Masonry Network website, you have countries and you have documentation related to performance or to confined masonry in these countries, and Chile is one of the countries that has been included there. So that is all for this presentation. In chapter 5 of the book, you could see photographs from different earthquakes and illustrations and explanations. I thought that it is interesting to give an illustration of the confined masonry building, or the case study of the Chile earthquake, since I had a first-hand experience visiting the country. And I also had opportunity to collect that information and could give some comments. So in addition to that, this performance of confined masonry is well documented in other earthquakes in other countries, not only in Latin America, but also in Europe, in Asia. And as I mentioned, that is it. So this would be the end of this particular presentation of the topic of performance of confined masonry buildings in past earthquakes, and before that on the behavior of confined masonry buildings, and a little bit of exposure to the testing, shake table testing. So thank you for your attention. Any questions about this? Yes, I see a hand. Can you see me? Can you hear me? Hello?
Mr. Ronak Motiani, please, you can continue.
I cannot hear you.
Hello. Professor Ronak Motiani, do you have any question?
Sir, I've given you the permission to unmute yourself. Ronak, sir.
Maybe ask the question in chat if you want, Ronak. Hello?
Ma'am, I think he has some issue. Just a minute. Any other participants who want to ask the questions,
In
they
the
can
meantime.
ask the questions meanwhile. Ronak, sir, you can unmute yourself.
Thank you, Dhruvi, for giving me the right. Thank you. Good morning, ma'am. And
Good morning, good morning.
ma'am, I have so few basic doubt. If you permit me to ask a question, a very basic
Sure.
doubt I have. Ma'am, I was just thinking about the dimension that we discussed yesterday. You told that the column was about 230 mm by 230 mm tie
That's
column, and even it can be lesser than that. Ma'am, in such a column, suppose if I roughly assume that it is 20 centimeter by 20 centimeter column, what is the permissible height by which I can do the concreting work? Because if such a small height, I think so the concreting has to be done with a height of 3 meter. Or is there some restriction? Because IS 456 says that the concreting free fall generally should be 1.5 meter, that is half of the column height. But with this small space, specifically at the corners, is there something that can be practically addressed to have a free flow of concrete?
Yeah, that's a good question. If you remember yesterday, I believe when I talked about GIAN construction, I showed two cases. In fact, I showed one case where you could see that tie column was constructed up to half height. So initially, the specification was given to the CPWD engineers, or they gave specification, in other words, to construct half height because of the concern of that. And then they concluded that that slows down the construction process, and they felt after some time of, because there's so many buildings, confidence that they could do full height. So it is either done half height or full height at the story level. If the confidence is not there in the sense of construction quality and ability, let's say capability of the site, then certainly half the height is recommended, because that gives so let's say 3 meter height, 1.5 meter. That's exactly what you're saying. But I would say that the idea is to if needed, to even modify the concrete mix to use a smaller aggregate size, rather than increase the size. That would not be my suggestion, to increase the size of tie column to be more comfortable with concreting. My other concern is not only that, is when you have this, as I mentioned, 135-degree hooks with full size according to IS 456, which actually has to be according to that has not been changed, that they are sticking inside, they're going inside the cage, and they're somewhat obstructing, not too much, but they could obstruct as well. So what I want to say is that these are two things. One is, pouring concrete, and the other is internal obstruction within the cage from these hooks. So far there is no confidence in India that 90-degree hooks would be good, because still there is the memories of columns. But anyways, that is not that big as far as I know. And today we'll have Mr. Anal Shah. Okay. So he will be able to say firsthand, because he was going to the site and he was from day one experiencing all these things as as engineer. They called him on the site. So anyways, I would say that in initial stage of application, or for first application of confined masonry in any project, it would be good to go half height, because certainly, but it does slow down the construction speed.
And ma'am, slowdown is also an issue, but with half a construction area and with that small pouring of concrete inside with a manually is really tough. on a practical side. With if it's RMC and pipe is going inside, it's easy, but manual, because for this, we have a small quantity of concrete for this work. So then the pouring will maybe an issue. That's what I was
Yeah,
anticipating.
yeah. But at the end, what I'm saying,
Yeah.
okay, ITGN campus may not be the best example because it's a large government
Yeah.
project, or not so large. I mean, in India size, but relatively large. Let's put it that way. But in general, it could be done, and I've not seen any construct. I cannot say that, for example, for
True.
Chile, even though I spent 10 days, I've not seen concrete construction, so I cannot say what did they do, but I've seen in the codes of various countries, they say you can do half height or full height. That is simply the recommendation, or two
Because, ma'am,
options.
as a structural engineer, whenever we say something, site people direct start blasting on it that you do not know how we'll do the concrete, and then they ask us how to
Yeah,
do it. It's really difficult to defend. Ma'am,
yeah.
second question I have pertaining to the geotechnical issues. That is again a basic question which I have some little bit of confusion. You said that geotechnical issues are required to be taken into the consideration, and specifically that was a cause of failure. Now, if we see the confined masonry building, they are generally of a 4-story. So I suppose the time period which they will have will be less than 0.5 second or close to that. Now, pertaining to the response spectra that is suggested by IS 18931 2016, that lies in the constant acceleration zone. So there is a flat line. So I suppose it will give the same values of spectral acceleration for soft soil, medium soil, and the rock,
That's
because
right.
it's 2.5. Then, ma'am, does I have some, then does it mean that the design will be same on the soft soil, medium soil, and the rock soil?
Yeah, it will be the same, but you see, I'm currently working on one similar problem, not related to confined masonry, but I'll explain how it is similar. If there is a geotechnical soft soil condition, and this is a rigid building, what will happen is that the only way you can capture it is by soil structure interaction, by
Definitely.
modeling it with the springs. So I was going in that direction because it is like a box. And if it is like a box and you have soft soil, you will have a larger displacement. So you have a change of demand, but you cannot see it by the spectrum.
Definitely.
It can be captured only by the model.
Ma'am, actually for this problem, I did site-specific study for this reason. I
Okay,
generated
excellent. So
synthetic ground motion. I did
yeah,
MSW testing
yeah,
to
yeah.
get the results, but then the result were too much different from IS codes. I'm not sure whether my results are right or not, because it is having so much deviation.
Yeah,
Then it is not matching. So it is, whether it is correct, will it have deviation theoretically?
Yes, I'm now doing. In fact, I share with you the paper when I submit it. I'm writing now the paper for the European Conference on Earthquake Engineering, but it is about not confined masonry building. It is another type of stiff buildings. These are precast wall buildings in which we have here in
Maybe any
Europe.
building, but ma'am,
Yeah,
will it
yeah,
have
and
different performance on the
it
soil?
will have, if it will have different, but
Theoretically,
it will
it
have different performance. It will have much higher displacements. It will have, then displacements will cause higher forces and all that. It will have a different performance. But right now, of course, in the Indian code for confined masonry, it is not addressed. Neither, I think this is what I've showed is an interesting case simply to you. I mean, I shared it and it was on top of the hill. So it
yeah,
was
it was a sloping
amplification,
ground.
sloping ground. So it was amplification due to that at the location. So this is something, again, it's not captured by normal design. So you have to do specific studies. So
Specific study.
it will give, and in Canada, in Europe also, it says that if you have site type E, let's say, if that is the worst case
Yeah,
scenario, you are
that is
supposed to do soil specific study, and whatever that study gives you, that is the result. So if this was that type of soil, then the study should have been done. But as I said, this is social housing. They didn't do any study. They just constructed them and designed them in the same way, no matter where they are. So I doubt that any attention was given to that. And again, who would say that they would have 8.8 magnitude earthquake that was just like 10 kilometers from that place? So it is again extreme. None of these buildings was designed for magnitude 8.8 earthquake. So it is
exactly.
a excellent performance given the earthquake. So, but yes, the results of soil study are going to be way different from any code. That's for sure.
Uh, one last
That's
question, ma'am, if
yes.
you permit.
Yeah.
Ma'am, if we talk about Indian scenario, you are aware that majority of the Indian the population in rural areas are having a masonry house with I think so some of them have the bends also and half of them are the without bends also. Ma'am, out of curiosity, I have had one question. Can existing building be converted to confined masonry? Is it feasible or it is a difficult job? Because the IS code for the masonry, which you were saying, says that we can provide band with grid,
Yes.
and then bands can be provided. This is how they have measures to safeguard the existing building. But can this, will it be feasible to, or can it be thought of an existing building converted, or maybe of a ground story, ground plus one story, or even of a ground story, be converted to confined masonry if we can have a column at least at the corners? Uh,
Listen.
is it possible to do it? Will it?
That is a good question, and of course, it would increase safety. Let's say in area like Bhuj, and we are talking about high seismic areas. If you're talking about Ahmedabad area or villages around, then maybe not that important in zone 3, isn't it? So let's say, but let's say Bhuj area, if they
Yeah.
don't have it. So I think it is difficult to put. You can put tie beam at the top. That is not a problem to make a robust beam at the, which is very important because we said that one of the key things with masonry is that box
Bend.
section. So
Box
if you
section,
have this tie beam, solid tie beam, which is really robust, not like lintel band. Lintel band sometimes can have only 2 bars, isn't it? So it is not the same. But this is like with the 4 bars and with the like proper beam, like shown here. That would be good. But the problem is how to introduce the vertical elements. And one option would be if the building was done using, let's say, bricks, but in some low strength mortar, it would be possible to reuse these bricks, to demolish the building from the plinth level and to reuse the bricks and then construct the reinforcement and do it. Or, but I think externally, the only way that you could do if you want to introduce tie columns, you cannot actually introduce tie columns because you would have to remove the corners of to remove bricks
walls.
in the corners, and how to then embed the reinforcement at the bottom. The only way would be then to externally strengthen corners with, the technique well known
Mesh,
with wire mesh and
wire.
that. So I would do rather that. But I would, if it was my house, I would construct, if it is already a timber roof and all that, which can be removed and reconstructed, not demolished completely, but reused. I would put a solid tie beam on the top, and I would strengthen corners with external reinforcing with wire mesh and like reinforced plaster technique, because that would already be not equivalent completely to this, but it would be much better than just pure unreinforced masonry, because who knows how these intersections were constructed, whether there was a proper bond and all that, or maybe one wall was constructed first and then the second wall was constructed later. So there is a vertical joint, and so in fact there is no integrity to start with. So I think at the minimum that should be done, and it could be done because that does not require destructive intervention.
And ma'am, this toothing element that plays a very important role in confined masonry, the toothing
Yes.
part. Ma'am, if you talk about the same concept, I think so it is implemented in RCC also now. Many of the RCC buildings are also having the toothing part of brick masonry. Is it desirable in RCC? Will it change the failure pattern of the masonry in the normal frame structure, or it is not desirable in that regard? Ideally, it will have a good bond. So, uh,
I think it will not change the behavior in RC, because still, if you have the frame as load-bearing system, this masonry will work as a strut. Whether it has toothing or not, it's not going to be. Here, we're talking about system which does not have a load-bearing. The frame is not load-bearing system, so there toothing is important because these are just two parts of the same wall. One is in reinforced concrete because it's not possible to reinforce masonry, as we discussed, in that vertical direction. So that's why it is reinforced concrete. It was possible to use masonry. Masonry would have been used. So, and then this. So that is internal. I'm not aware of this toothing for reinforced concrete, but you see, the one of the reasons that the toothing may be used for reinforced concrete frames with infills is out of plane behavior.
Yeah.
Because
Maybe
for out of plane, this toothing will help better performance and prevent falling out of the walls at the higher, really, if there is a high intensity earthquake. What happens with the walls? I've seen that in Albania in 2019. Severe damage in out of plane. So out of plane could be very bad performance for this infill. So this is not for in plane. I think these two things may be for out of plane.
For
out of plane. Yeah, they're good questions. So thank you.
Thank you, ma'am. Thank you so much.
Any other questions? Most welcome, Deepa Raval, I think. And Deepa, please go ahead. I cannot hear you. Again, maybe muted. No, voice is not coming.
Sorry.
Okay.
The question is like, as we saw many times, the failure initiates from the between the interface of tie column and masonry. So is there any way we can think of to make that load transfer smooth by using the concept of functionally graded material like kind of thing, or some intermediate stiffness lamina kind of thing?
I think this is simply mechanism of failure, and that will be because these are two different materials. So I don't think there is anything would change, because you see everything starts from masonry. The only thing that can happen is that you have a stronger masonry and this is delayed.
Okay.
But you see, if you have one path that you are going, let's say even if it is a road, you can take a shortcut, but your goal is the same. So you can take, take a side street and you want to still come to the same goal. So that is not simply, this is a basic mechanism of behavior of masonry, and that cannot change because that is what it is. The only thing which we can do by choosing if we are possible for us, stronger materials, is that we have a higher strength masonry, or we have more walls. That is what we control through this wall index or wall density. And but the mechanism, Deepa, we cannot change, and it will at the end, by propagating from masonry, it has to go to tie column. But in this case, tie column is a part of the masonry. It is a part of the same wall. So it is just a stage in behavior. And good news, really good news about it, and based on the testing, is that at the end, even though that crack looks ugly, there is no really collapse. There is no collapse.
Yes.
So in reality, even if you have that ugly crack after the earthquake, it could be repaired. It could be repaired as long as reinforcement has not been damaged, and like concrete can be replaced and patched up and all that. So if there is a very heavy damage, a wall ground floor level of a wall can be also replaced if needed. Why would you replace the whole building if only ground floor is damaged? But I believe that it could be repaired. In Mexico, for example, what they used as a repair technique, I have not talked about that. Now this whole course is about new construction. But in Mexico, they use techniques with what I just talked with Ronak, with wire mesh reinforcing of entire wall, and and then plastering and grouting the cracks. So they have experience, obviously, in earthquakes with the damage of confined masonry buildings. So various techniques are available, but mechanism is such, it is just, that is the mechanism. Like in concrete, you have shear failure, flexural failure. In masonry, this is how shear failure looks like, and it's simply the crack will propagate. But toothing is important. Toothing is important to make them work together, because these confining elements are really critical, not so much because of to improve the strength, it is more to improve integrity of the walls. And if you don't have the toothing done right, with either way, with by toothing physically or by reinforcement, then we have a problem, and this will be different behavior. But it's a good question. You are looking for ways to improve the system, and who knows, maybe there will be some innovations there too. But that is my opinion for now, at least. This is the best I can tell.
Thank you, ma'am. One more question was there. Like in case of normal slab resting over a beam, we don't need to take a special care in case of we are transferring load from secondary beam to primary beam. But in case of confined masonry, do we need to provide some special arrangement, kind of wall template, or anything is required to for a better load transfer from slab beam, which is supporting some slab or any other
But
load?
you see, no, nothing is required. In fact, here, if you looked at these photographs, and I encourage everyone to download that publication because it's available on the website of ITGN, how that was constructed. So simply on top of the wall, you have directly beam constructed. So tie beam. So there is no, and that beam becomes a part of the slab, isn't it? So because that is integrated into the slab. So simply the concrete is cast, the reinforcement is put on the top of the wall, and then concrete is cast. And then there is direct, because of the gravity, like how the concrete pours, there is no need for additional connection between that top of the wall because there is no gap. Simply concrete is poured and all the weight of the slab goes onto that wall by itself. There is no need, so there is no gap at all between those. So there is no need for any physical connection, if you meant, between the top of the wall and the slab. No, nowhere in the world. That is simply because it is just integral. It is going just on top of it. So there is no tooting or any other needs for that. And it didn't show any problems in the earthquakes. That location is not showing any separation, like whatever you would think of as happening, like horizontal separation, which I've seen in many cases in India. And below the slab, at the floor level, you can see the horizontal crack. That might have happened maybe due to some shrinkage as well. In masonry buildings, I've seen it after earthquakes also, but it could be also part of the construction practice. But in confined masonry, I've not seen, or not that personally, not seen in reports any horizontal cracking at the interface between the top of the wall and the slab, and the tie beam, actually. That's right.
So we take care while designing the tie beam of that roof.
You don't take care of anything. You just it is just a matter of construction. So there is no design feature because tie beam is just constructed on top of the wall. So it is just a lint. It is just like a lintel. It is actually exactly. That's right.
Yes.
That's right.
Thank you very much,
You're
ma'am, for
welcome.
clearing this doubt.
You're welcome. Thank you, Deepa. So any more question? I think there is
We
more
have
question.
one more question, ma'am. Last question from Ronak sir again. Yeah.
Ma'am, in continuation to what Deepa madam asked, you told that some of the cracks are ugly but still can be repaired. Ma'am, in particular to slide 26, you were explaining two types of crack. One was a plaster crack, and in the same part there was a crack on the masonry. Ma'am, if it is possible, can you explain that point again? Because there's a little bit of confusion. I have a slide open with me. If you can just say it will be also fine.
I can open it. Yeah, maybe because of other participants. I can share quickly. That's okay. No problem. Hopefully. So let me see. Can you see my screen now?
Yes, ma'am.
Yes, ma'am. Slide 26 it was, ma'am.
This one?
26, yes, ma'am.
Okay, so I'll leave it here. So these are cracks in plaster, that's right. So in the middle one, because it is a pier, see, there is a crack. There is also plaster crack, and but there is also, if you look at this portion, there is also crack in the bricks. So again, what would be the repair technique for this? Would be to possibly grout this crack, but more importantly, to put reinforcement, to apply wire mesh and reinforce this, because this is shear cracking. And if you apply wire mesh, attach it to the wall with some anchors, and then apply some either shotcrete or some 5 centimeter of some fine concrete, that would be the repair technique. So it would not need to be demolished or anything. It could restore, because the technique is very effective in and it could be done double-sided, both exterior and interior, and that would be repair technique. And I would assume that that's what they would do. So because of these cracks, they wouldn't demolish the whole building. Obviously, there is no justification for doing it. If you know, when you have this location of the wall going, you've seen in that building, red building in Kokenes, that's really, I mean, what to do there? It's really okay. The upper floors are okay, but this is such
Ground floor is a
heavy
critical.
damage, so heavy damage. It's just close to collapse that they vacated the building. But this case, this is all repairable damage. I would say out of stages 1 to 5 of damage, this would be 3 to 4 maybe, but it could be repaired.
Repairable damage.
Repairable damage. And in this wall, in the middle, you see there is a tie column. So this was on the side of tie column the crack happened, because there was a cross wall behind it. So in the middle there is a concrete portion which is tie column, but this brick portion is masonry portion is damaged, and it could be repaired. And the fact that there is a tie column in the middle will help, because there is a concrete reinforcement inside, and it would, like when you put it all together, it would be really nice element afterwards when it is restored. It would fully restore and even improve the shear capacity of that wall, because I would say that shear capacity was low because it's a poor quality, low strength bricks, and a poor quality of construction. In this, it is visible in this case. So we have to use our judgment on a case-by-case basis, but if the thing comes to extreme damage, there are some points where there is no discussion on what can be done, just demolition.
Thank you, ma'am. And regarding that soil amplification part, if you don't mind, I'll write that email of the results that we have got. Can you please, ma'am, just comment on it?
Yes. And send me an email, please. I want also to share that you were asking about that non-destructive testing technique.
Yeah,
I'll share with you so you can share with others. I don't want to share everything. I've shared so many documents. I think it's
No, it's
overwhelming.
really helpful, ma'am. You have made confined masonry look very simple. It was a very complex part before this workshop, but after this, particularly with the last lecture of the designing, it was really interesting that yes, we can do it. It was really impressive, ma'am. Thank you so much.
And then it would be much simpler if I after that give a lecture on IS 13920 and you have one by one. Then you can see this confined masonry is nothing compared to concrete.
It's very easy and very effective also, ma'am. Very easy, but because we do not know it, it looks very complicated. That would prefer the routine procedure. But I think so after this workshop, we'll definitely have and cutting edge over that.
Spreading the knowledge, and I hope that those among you who are professors at colleges can use this material for training. And I'm happy to share source presentations if needed. There is no problem with that. Now, right now you have PDFs, but if that would help, we can have a repository of materials which could be used for training of teaching.
Sure. Thank you, ma'am. Thank you so much.
Yeah,
thank you.
You're welcome. You're welcome. I want to share knowledge. Thank you. Any more questions? I stop sharing now. Any more questions? If not, then we'll take a break, and I will do second session on out of plane. There is a change in second session. Maybe do you want me to announce a little bit of change, not too much, but a partial change. So any questions? If not, I would just like to announce that in the second section, I will first talk about out of plane resistance. Chaitanya, do you want to mention that, or do you have questions?
Yes. So there is a slight change, and we have a session. Initially, the session will be handled by Dr. Svetlana Brezev, and she will talk about the out of plane failures. And around 1 o'clock, Mr. Anil from NK Engineers will join, and he will share his experience of the first confined masonry application, large scale application in India at IIT Gandhinagar. So he will share about his experience at IIT Gandhinagar, and then this session will conclude, and after that we will start our validatory session around 2 o'clock, and then we have a feedback session by the participants, and we all will share our experience of this STTP. In this validatory session, we have additional guest of honor. We have Dr. Vijay Shah, who is the principal of LD College, GEC Morasa, along with the principal LD College of Engineering. Professor MC Chudasama is joining. He is a GIAN coordinator, and we are also sending we have sent a mail to IIT Kharagpur if any GIAN official will join from IIT Kharagpur. So we have a validity session around 2, and in that we are going to float the quiz. So participants have to go for the quiz, and we'll give some time. The announcement will be made regarding the quiz at that moment. Right. So thank you.
Thank you, ma'am.
Now Dhruvi. Yeah.
Yes. Thank you, ma'am. Ma'am, also I wanted to know that one last thing. When you send Ronak sir the email, can you also send the paper that you are going to send on the scrape test in New Zealand that was done? I think so. We discussed it on day 3 on the scrape testing. When sir asked about the prism testing, you also mentioned about the scrape testing that was done in New Zealand. The paper
Okay.
related to that. If it's possible.
To
I'll
share
just
with
send
all
you.
participants. That is okay, because I
It's
thought
okay. I'll
that
just
all
email
would be
you
interested
asking for
in
the
that.
paper. Yeah.
Okay. Okay.
Yeah,
No,
thank you.
no, I can share that with everybody. And I shared also, I don't know if you received if Chaitanya had a chance to share this full example on white column model in SAP, including a SAP.
Yeah.
Oh. Mhm.
Yes.
Yes,
That
it is
was
shared
done
with the participants. Yeah.
You shared, okay. So it is a older version of SAP because it was shared at the 2014 short course on confined masonry. So I'm not sure which version of SAP it is, but it should be able to open it, and it gives a 3D model with white column model as presented on Wednesday. But he also shared at that time the SAP files, which is very useful. So okay, yes, I will share that testing. I'll share a link to that. It is free document on the New Zealand government or whatever organization website, but I will explain what it contains, and I will share a link. So it's best if I share a link, so then you always have that access to that
Yes.
document when you want
Thanks so much.
read to find it. So when are we going to start the next session?
We'll take a break of around 10 minutes.
Okay.
Okay, then all the participants will be joining again at around 12:10. Let's take a 8-minute break and round it off to 12:10. We'll send you the link in the.
And we use different link. We use different links.
Yes, ma'am.
Yes.
For session 2. Okay. I will join. See you soon.
Thank
Bye.
you, ma'am. Thank you.
Thank you, ma'am. Thank you.
Thank you, sir.